So I'm going to share my screen for you. Yeah, so I guess you can, all of you can see my screen. And remember the last time I so we talked about galaxies and different properties of galaxies, and as well as structure of our own Milky Way. And so let me switch off the video so that you can. Right, so I'll stop the video so that you can connect easily. So we were right here last time. So remember we talked about different types of different properties of the galaxy and different types of galaxies, and then the Hubble classification, how Hubble has classified galaxies depending on their shape and also the ellipticity. And there was basically two types of galaxies, ellipticals and spirals, and in between there is a type of galaxy that is called as S0. And then these spiral galaxies are divided into two sections in that tuning fork diagram. One section is about, I guess, having these bars in the spiral arm, and the other section is the spiral galaxies that without bars. And along each arm, they are divided based on how tightly these spiral arms are wound in the galaxy. Right? So that's the idea about classification of galaxies. And then I told you this slide right here that you see that galaxies are also divided into two sections called giant galaxies and dwarf galaxies. This is mainly based on their size and the mass. So if a galaxy is smaller in size and smaller in mass, they used to call as dwarf galaxies. And then if you have larger galaxies like our own Milky Way, we call those type of galaxies as giant galaxies. And remember that these two are two different classifications, not the same. And then I gave some of these examples for dwarf galaxies. And dwarf galaxies also have another name called satellite galaxies. And as of now, we have around 16 dwarf galaxies around our Milky Way, right? So this is about galaxies. And then these Magellanic clouds are also the small Magellanic Cloud and large Magellanic Cloud are two famous dwarf galaxies which are close to our own Milky Way. And this is actually one of the nice pictures that shows you this telescope is actually called a CTIO telescope, which is located in South America. And this is in Chile, actually, in one of the mountains. And this telescope right here is a 4-meter telescope. So what that means when I tell like 4-meter telescope is the diameter of the primary mirror of this telescope is 4 meters. And when you tell some details, when you tell someone I have a 4-meter telescope, if you are an astronomer, they used to get an idea about what kind of things that you can look at from that kind of telescope. Now 4-meter means it has a very large mirror, and this increased the light gathering ability. And when I looked at your notes for the chapter 1 and 2, I saw that there was an equation written for the light gathering ability. that is called as I guess 5d squared over 4. And the idea is, if you need to compare two telescopes, let's say you have a telescope with 2-meter diameter and one like 4-meter diameter. So what this means is, if you think about the light gathering ability, is roughly proportional to the d squared value. You can see that 5/4 is the constant here. For the d squared value, d is the diameter of the telescope. So what that means is, this 4-meter telescope, 4 squared is 16 and the 2 squared is 4. So that means the 4-meter telescope has a light gathering ability that is 4 times larger than this 1-meter telescope, right? So that's the idea. So that's why we used to normally mention telescopes in this way. And all these telescopes are reflector telescopes. And I also saw that you have talked about these two types of telescopes. One is called refractor and the other one is called reflector. And these large telescopes, they are actually reflector telescopes. So they have a primary mirror that gather all these light, and then these are like curved mirrors, and then they will be focused to a particular point, and then you have a CCD camera at that particular point which will capture all the lights, and then there is a process that CCD camera take all these photons to a computer through an analog digital converter, converting all these signals to digital signals, so that you will see an image displayed on the computer screen. So that's what will happens actually practically. In this particular image is that this actually showed up a very nice picture when if you go to this particular place, Chile. So I would expect that one of you may go there in future. If any of you like doing astronomy, you may have a chance to access one of these telescopes. This band of cloud right here that you see is actually our own Milky Way, right? And then you can see that there are two galaxies right here and here. The Milky Way is one that is in the right, and then these two are actually large Magellanic Cloud and the small Magellanic Cloud. These two galaxies, the two dwarf galaxies that you see. And unfortunately, if you are in the northern hemisphere, it is very hard to see those two. So these are like galaxies normally visible into the southern hemisphere, right? And the sky need to be really dark in order for you to see these kind of galaxies up in the sky, and also you should with a telescope, right? And that concludes the details that we talked about galaxies very briefly. And then let's go into the next stage. And remember that from the beginning of this course, you have probably talked about planets, and then we talked about the stars, and then we have talked about galaxies. Now we are going to talk about galaxy groups and galaxy clusters. Now, galaxy groups are actually, when we look at the universe, we find that galaxies are not at random throughout the universe. So they are actually also not isolated. So what this means is galaxies like not distributed randomly, right? And most of these galaxies are found in groups. So there are several locations on the sky that you see group of galaxies. So they are not isolated. And most of these groups contain at least two giant galaxies and maybe some other several dozen two giant galaxies and maybe some other dwarf galaxies. And actually some of these groups will have maybe dozens of giant galaxies. So there are no specific numbers that how many galaxies that you should have inside these groups. Now, these giant galaxies normally accompanied by a set of dwarf galaxies, as I told you. So a group is a collection of giant galaxies plus dwarf galaxies. So if you have a group of galaxies that you can see up in the sky in a particular location, we used to tell that that's a group of galaxy or galaxy group. And they are basically located in that way due to the gravitationally bound. You know that if you have large masses, they used to have gravitationally bound each other, right? So inside the galaxy group, everything is gravitationally bound to each other, so that you will see them as a collection of galaxies. And now let's look at our own Milky Way. So our Milky Way and its all satellite galaxies, remember that we mentioned that there are 16 of those satellite galaxies in the Milky Way. So all of them are actually belongs to a group called local group. And this local group actually dominated by two giant galaxies, the Milky Way, which is our own galaxy, and the Andromeda galaxy. So these are the two galaxies that belongs to our own local group. And apart from these two galaxies are actually separated from 2 billion light years from each other. And each of these large galaxies have smaller number of dwarf companions. And overall, the local group has more than 40 galaxies. So some of these have been discovered in very recent years and have yet to be confirmed. So there are still galaxies that have discovered even in our local group, right? So remember this name, the local group means the group of galaxies that we belongs to. And we basically have these two galaxies, Milky Way and Andromeda galaxies, as giant galaxies inside this local group. And apart from that, there are more than 40 other galaxies that belongs to the local group of galaxies, right? So there are some other pictures that I have actually put here, which I will be not talking much about those. And so that's about group of galaxies. And then we go into the next scale of the galaxy, which we call as cluster of galaxies or galaxy clusters. And when you have galaxies that are found in large groups, so remember in these small groups, we have like 40 galaxies, those kind of number. But if you have galaxies that are found in very large groups, we call them as galaxy clusters or clusters of galaxies. And inside these clusters, actually, there are a large number of galaxies. And there are some galaxy clusters that have 2,000, 3,000 galaxies inside that particular galaxy cluster, right? And actually, inside these galaxy clusters, we have a vast range of galaxies. So they are in different sizes. The galaxy clusters actually have different, they come in different sizes and richness. Richness means if you get a particular galaxy cluster, if you have large number of galaxies inside that galaxy cluster, we used to tell that it is a rich galaxy cluster, right? And there are actually ways that you measure this richness, different equations. And I am not going to talk about those as it is not in the scope of your syllabus. But basically, for the galaxy clusters, they have they comes in different ranges and based on their size and the richness, which means how large the cluster is and how rich, which means how many galaxies are there. If you have a large number of galaxies, we used to tell that it is a rich galaxy cluster. And these galaxy clusters are actually typically about 15 million light years in diameter, and you can see the number, right? Now, if you take our own galaxy, it's like 100,000 light years in diameter, right? Yes, it is just one galaxy, but if you get these large galaxy clusters, they are around 15 million light years in diameter. And in the richest cluster, you will have thousands of galaxies, right? So which means sometimes you have 2000 and 3000 galaxies. And in fact, I have observed data of around 10 of these galaxy clusters. And I remember that some of these galaxy clusters have like 3000 galaxies in one of these clusters, right? And if you get one of these rich clusters, they have very high density of galaxies, especially in the central region. And this is one feature that you would see if you look at a galaxy cluster. That is that close to the central region, you will used to have large number of galaxies. And when you go outside, let's say you define a radius. So let me draw it in this way. Let's see, this is the region of your galaxy cluster. And if this is the center of the galaxy cluster, and when you go outward, typically in this region, very close to the center, you will have large density of galaxies. And when you go outside to the outer region, the number of galaxies normally goes low. And most of the bright galaxies are ellipticals. Now this is something important. And close to this central region, you have a lot of elliptical galaxies, and O is zero galaxies. And another thing is, in most of these galaxy clusters, you used to have one very bright galaxy at the center, right? We call this as a giant elliptical galaxy, and there is a specific name for this galaxy at the center of a galaxy cluster. We call that as BCG, or brightest cluster galaxy, which is actually not mentioned in here, but just for your information. Right, so this is an actually example of one of a rich galaxy cluster, and the name of this cluster is Abell 426. Abell 426. You don't have to remember these numbers, by the way. So this is the name given as Abell 426 because it comes from the Abell Galaxy catalog. The reason that I remember this name is because I personally observed these galaxies. So you don't need to remember these galaxy names. What I want to show you here is this. This is the brightest cluster galaxy, or the BCG galaxy in this particular cluster. And you can see that that is very bright and at the center of the cluster. And all these objects, this one, and all these are actually elliptical galaxies that are very close to the center of the galaxy cluster. And you can see that these are real, right? So this is an image that I took myself from this large 4-meter telescope in K.V.S National Observatory. And all these galaxies, these are all galaxies, right? This one, all these are galaxies. And I used to get this question from students when I'm doing about these galaxy clusters, that when I tell that all these are galaxies, they used to ask from me that how can you straight away tell that? And actually there are ways that you identify galaxies and stars, because there are stars, large number of stars in this image as well. So you need to separate stars and galaxies. And there are different techniques for those. And one straightforward is, you can see that galaxies are actually extended objects like this. If it is a very bright galaxy, you can easily see it. But there are some dwarf or small galaxies that you cannot differentiate those from stars, right? And then there are statistical procedures and some other ways of doing those. But let me not go into that section. But if anybody need this knowledge, contact me later. You need to know something about those, so I will talk about those separately, but for the time being I will stick with what you need to learn in the course. So right, so if you take each galaxy cluster, you will see this. If time permits, I will, at the end of the lecture, I will probably show you one of the images as when it is in the real format. to a different software and will zoom into each of these galaxies and show. I can show you even spiral arms of some of these spiral galaxies in the galaxy clusters. Right. So this is the same image, by the way, ML426 taken by Sloan Digital Sky Survey, but the field of view is different, and this is that brightest cluster galaxy right here. And this is again another example for a galaxy cluster. And this galaxy cluster, the reason that I put here is actually this, I don't know whether you can see, there are arcs like this in this image. And these are actually as a result of a phenomena called gravitational lensing that comes in general theory of relativity. That is actually due to the bending of light when you have a huge mass. So basically what has happened is when you have a galaxy cluster, you have these large galaxies with enormous mass. When light passes nearby, they used to bend. And this gives a lensing effect. So you know that in physics, when you use a lens, what happens, right? So when you get that lensing effect, there is an opportunity that you can see things that are behind this galaxy cluster. So that's something extra, some extra details. And then after talking about galaxy clusters, then you have something called superclusters. And these galaxy groups and clusters that we talk, so they are actually not the largest structures. Largest structures in the universe are actually superclusters up to now. So the supercluster is basically collection of galaxy groups and clusters, as it mentioned here. And for a typical supercluster, so they contain actually lots of groups and some clusters. So which means they may contain tens of thousands of galaxies. And so the idea is actually you will have groups and clusters inside the supercluster. Inside is each group or each cluster, they may have tens of galaxies or maybe thousands of galaxies if it is a rich galaxy cluster. And now our local group, which we belong to, remember that we have Milky Way and Andromeda galaxy and some other around 40 galaxies that we have discovered inside this local group. And this local group itself is a member of the local supercluster. So we are basically inside this local supercluster, inside the local group, and inside the Milky Way, and inside our solar system, and inside Earth, right? So that's how we are defined, or basically our address, if you need to define, right? And the Virgo is the galaxy cluster that lies at the center of this local supercluster. Probably have heard about Virgo galaxy cluster. And the local group, which is our own group, is around 60 million light years from this Virgo cluster. So Virgo cluster is at the center of this local supercluster, and our own group, which we called as local group, is around 60 million light years away from the center of the local supercluster, right? At the center, you have Virgo cluster. So basically, we are basically right in the outskirts, which means outer region of the local supercluster. And some superclusters may have hundreds of billions of light years in diameter. So you can see that how large they are. So they are really huge entities, so probably units in cosmology or the extragalactic scale. And now that conclude about different structures that we have been talking, and apart from that, I have included a few slides here just to explain you what's going on in between galaxies. So these galaxies actually they are not isolated, so they don't live in isolation. As you saw that they are in groups and inside clusters. And what will happen is, in fact, sometimes they used to pass close enough to one another. And this will lead to dramatic changes, right? Now, the closer the two galaxies are, the closer the two galaxies are to one another, the stronger the effects will be. So what will happen is, the more massive galaxies will have stronger effects. And if two galaxies encounter each at high speed, then the effect is on their interstellar matter may be strong. And remember that, so what you have inside this galaxy, one of the inside these galaxies is you have stars and interstellar matter inside each galaxy, right? So when they encounter each other, what would happen is, probably I don't know whether I told you this, that it's what is more probable is that interstellar matter will get interacted each other, not the stars, because the stars are vastly separated each other, right? So there is a high, very low probability that stars get collide each other. Now, depending on how fast they encounter each other, in low speeds, the galaxies will be more likely to merge with each other, which means they will merge each other, not collide each other. And there may be other effects that can happen. Maybe you will have the most common type of encounter seen in this slide I have mentioned, in which the galaxy is in the same vicinity but having a strong effect on on one another. So they may be disrupting each other gravitationally, primarily through the tidal effect. So there is something called tidal effects that comes into play here. And so let me leave the rest of the slides in this lecture for you. Just go through and read through the slides. I guess mentioned most of the information here about different types of galaxy interactions. So, and as a result of these interactions, one thing that could happen is this will trigger the star formation. Or we used to tell that this can also lead to truncate or completely stop the star formation inside galaxies, which is actually one of the active field of studying right now. That what happened to star formation rate inside galaxies that are in the galaxy clusters, and also field galaxies. Field galaxies means the galaxies that are outside the galaxy cluster. Right, so these are some images that shows you merging of galaxies, and there are actually different mechanisms of this merging process. There is one called like major merger of galaxy. Sorry. And there are actually one example of this type of mergers is Milky Way and the Andromeda galaxy may merge in about 5 billion years. So after 5 billion years, we will not have two galaxies. Andromeda and Milky Way galaxy itself can merge together due to the gravitational interaction, because both are in the local group of clusters, right? And during, so one thing that I need to make sure that you know about this is that during a merger, the stars rarely collide with one another because the stars are vastly separated, right? It is the interstellar matter that will collide, and collision of this interstellar matter may trigger intense burst of star formation. Remember that when interstellar matter collide each other, you need to go back and think about that conditions that we talk to have protostars. Remember that we talk about this Jeans mass and the virial theorem to condition to have a protostar, which is the initial state of star formation, right? So if you have, depending on how these interstellar matter interact with each other during these galaxy collisions, they may trigger intense burst of star formation. And there is another term called galactic cannibalism. What that means is if you have a very large galaxy and a smaller galaxy, the smaller galaxy will be eaten away by the large galaxy, right? Sorry, eaten up by the large galaxy. And so that's called galactic cannibalism, right? And there I have mentioned some of the examples here. You can go through those. And if you have galaxies that merging happens with more than 2 galaxies, maybe 3 or 4 galaxies, then the phenomena will be different, and you will have something called the ultraluminous infrared galaxies. And this is also have a short term called ULIG galaxies. So you don't need to go into details for the exams for these things, but I just need to make sure that you have a rough idea what's going on in these fields in case any of you move into the research field of these galaxies. And this is one of the simulations that shows up what happens during a collision of 2 galaxies or merging of 2 galaxies. And you can see that these 2 galaxies are merging each other and then create a very violent phenomena. And then you have like one spiral galaxy in the left side. So some astronomers actually have research conducted and believe that some of these spiral galaxies may have occurred or created during these galaxy collisions or mergers. And remember this, the simulation that I am showing to you, they are actually real simulations that based on real data. And this is another image that shows up what will happen to a galaxy called cartwheel galaxy, as far as I remember, during a collision process. And this is actually a cartwheel galaxy that we believe that it has probably interact with one of these galaxies that are shown in the lower left-hand corner. And this image is actually taken from seen from the Galaxy Evolution Explorer or Galaxy satellite, which is basically detect ultraviolet photons, and also combined with some of the other images from the Chandra X-ray Observatory for the X-ray wavelength, and also Hubble Space Telescope and the Space Telescope for different wavelengths. And if you go back and look at my research presentation in the YouTube, which I gave you the link, it has actually some of these details about these galaxy collisions and how these things happen. And this is also a different phenomena that happens inside galaxies. When a galaxy actually goes through the galaxy cluster medium, there is something, a phenomena called ram pressure stripping that happens to a galaxy, which basically stripped away most of the matter. And this can lead to either truncate or trigger or start the star formation process again in the galaxy. And basically I have what I did in my research for my PhD was something related to this, how this effect of ram pressure stripping thing effect to the star formation inside galaxy cluster if you measure the star formation rates from central region to the outer region of the galaxy cluster, right? You don't need to go into too much details in these, but if you are interested, you can always go back and look at that image, the presentation that I presented, which is available in YouTube as well. These are some of the images, but I'm not going to go through it, but let me stop from here about the galaxies, the lecture about the galaxies and galaxy cluster. And we'll start the next or the last lecture about the cosmology. So yes, so right, for this section, we will start talking about cosmology. And under this, so what we will talk about the study of the origin and the nature of the universe itself. So that's the idea that I need to talk inside this lecture series about the cosmology. So first let's look at what kind of observations that we have about the universe. So there are a number of observations that can help us to learn about cosmology, right? Which is about studying the origin and the nature of the universe. So one evidence is the motion of galaxies, which can tell about the dynamical state of the universe. And it actually helps us to predict the fate of the universe, which means what will happen to the universe in future. And this large-scale distribution of galaxies tells us about the overall structure of the universe, and looking out the extremely large distances allows us to see how the universe has evolved with time. And let's see how we get this information, right? Now, the first thing is the motion of galaxies, which we talked about galaxies, but we didn't talk much about how they move in the space, right? Now, in 1912, there is an American astronomer named Westo. Actually, he tried to obtain spectra of many of the nearby spiral galaxies. So when he observed these spectra in the nearby galaxies, actually he called these as spiral nebulas because we didn't realize that they were galaxies at that time. Remember, I told this story for you in the last lecture about the galaxy. So what he noticed is that the spectra that he observed in these galaxies, they are actually shifted in wavelengths. And this was actually attributed to the relative motion between the spiral nebula, or you can tell spiral galaxies now, compared to us. So which results in the Doppler effect. So what he thought is that so when he observed these the spectra from nearby nebulas or galaxies, so he showed that all these wavelengths are shifted, right? Now he decided that this is as a result of Doppler shift effect. And what this means is, as you know from the Doppler effect, if something is moving away from us, the wavelength will be moved to the longer wavelength, which we used to call as redshift, right? If something is moving towards us, the wavelength moves towards the shorter wavelength, which we called as blue shifted. Now, what was surprise to him was that nearly all of the galaxies that he observed, the spectra that he actually observed, actually moving away from us, which means the spectra are actually red shifted, not blue shifted. Now, at that time, this was a complete mystery. Now, why this became a mystery is that due to the gravity, what we used to think is that these are all, the gravity is an attractive force, which means now all these galaxies that you see out in the universe, they should be attracted towards us from the gravity, which means they should move towards us, right? So that's the general idea that we have. And what happens is when you are in this idea that all these galaxies, if they are moving towards us, they should be blue shifted, not red shifted, right? Now this is why it became a complete mystery. Now, 1920, if you remember this story I mentioned before as well, Edwin Hubble used Cepheid stars. So Cepheid stars he used to decide the distance to the Andromeda galaxy, remember. So he used to measure the distances to many spiral galaxies, right? And what he found was that he found the connection between the distance to a galaxy and the size of its redshift. Now, previous astronomers found the amount of redshift from his spectra, and Edwin Hubble found the distances to these galaxies. And then what the conclusion was, there was a connection between the galaxy distance and the size of its redshift. Now, if you look at the nearby galaxies that have relatively small redshift, so nearby galaxies, we observed the smaller redshift, which are closest to us, even sometimes blue shifted. So there are instances that they have seen blue shifted, but most of them are red shifted. And this blue shifted galaxy is actually the Andromeda galaxy, if you need to remember, right? And all of the galaxies that they have observed are red shifted. Now, blue shifted means Andromeda is coming towards us, right? But other galaxies moving away from us. And Andromeda is, of course, keep in mind that it is the closest large galaxy for us. And the distance galaxies that they have observed has relatively large redshift. So the smaller galaxies have a smaller redshift, and the smaller galaxies mean the nearby galaxies have a smaller spectral redshift, while these galaxies that are far away has larger redshift. Now, on average, the redshift is directly proportional to the distance. So that's what he has identified. Now, one thing that I guess you can understand is that once you measure the redshift, that can also use to find the recession velocity of that particular galaxy. So, which means the redshift has the relation between the distance with the distance. The recession velocity will also have the same relationship. Now, this relationship is what we now call as the Hubble's law, which is one of the major findings in the field of cosmology, right? So this is what Hubble has found at this time. His time in this x-axis is the distance to a galaxy in terms of megaparsecs. So which means, and the y-axis is the recessional velocity of a particular galaxy. Now, for example, if you take this particular data point right here, that galaxy, the distance to that particular galaxy is very close to 3 megaparsecs, maybe a little bit less than that. And the recessional velocity is close to 2000 kilometers per second. And if you take a galaxy that is far away, let's say this one right here is 30 megaparsecs away from us, roughly. And that has a recessional velocity about around 15,000 kilometers per second. In that way, what has happened is there is a linear relationship according to this graph. The relationship is that galaxies that are far away from us moving faster, or moving away from us very faster than galaxies that are close by, right? And this is called Hubble's law. And this is what he has found. Actually, I basically explained it in the earlier slide as well. The most straightforward interpretation is that the space between galaxies is expanding in the uniform manner. In other words, universe itself expanding. Now, this is the first major evidence that we have to tell that the universe is expanding. The reason is that the galaxies that are far away from us, actually they are moving faster. The galaxies that are close by us, moving very slower. Now, this effect is completely not basically because we have this gravitational effect between galaxies, right? From the gravitational effects, we would expect that all the galaxies will move towards us, right? But there is something else going on. And that is what we call as the universe is expanding. And the evidence comes from this Hubble's relationship. And further away the galaxy is from us, the more space there is between us and that galaxy. This means that there is some intervening expansion. This will give the higher recession velocity. Even though the galaxies appear to be moving away from us, we are not at the center of the universe, right? So these are basically some of the facts that we reveal using the Hubble's law. Now, what actually happens here is, you may be wondering what's going on here in terms of the expansion. It is not actually the galaxies that are moving away from us. It is the space itself expanding, right? So the galaxies are on the space, and due to the expansion of the space, they seems to be moving away from us. This is what we call as the expansion of the universe. And if you need to think about this in terms of example that you know, think about a meter ruler that is made of some material that you can stretch it, right? Now, if you think about the distance between the 1 centimeter line and the 2 centimeter line, if you stretch the meter ruler, those two lines that has mark 1 centimeter and 2 centimeter mark, so those two marks will stretch itself, right? So that doesn't mean that one is going away, one is like moving away with respect to the other. It's like the space between that is expanding, right? So that's what has happened here for the galaxies as well. It is not that the one galaxy is moving away from us with respect to the other. It is the space that is expanding. And this is just an example what's going on here. And in the first place, right here, this is where the image we are very close to the Big Bang right here, which means that explosion of the universe, and after that, universe get expanded, and we are moving away from each other. So that means the space is expanding. You can see each circle is larger than the previous one. So the space is expanding. Therefore, the distance between galaxies are expanding, right? So as the universe grow larger with the time, the galaxies move further and further apart. So this is what happens. And that Andromeda galaxy, since it is very close by to us, the effect of the gravitational attraction is greater compared to this expansion. So that's why it has a blue shift. And here is another example using some pictures. You can see all these points are very nearby in the first one, and when this is a balloon. So when the balloon get expanded, all the points are moving away from each other. So this is what happens in the expansion of universe, right? And this slide actually basically summarizes what I have mentioned up to now. Already things like atoms, people, and stars and galaxies are not expanding. So these entities itself are not expanding. These things are actually held together by their own interactional force, right? Atoms from the chemical bonds, and the galaxies due to the gravity. So the gravitational force basically plays the primary role there. Now, even between distinct galaxies, the expansion is noticeable only at fairly large separations, right? That's one thing. The small separations, the relative motions of the galaxies are generally dominated by the gravity. So this is what happens for the Andromeda galaxy. For example, Milky Way and the Andromedas are actually moving towards each other due to their mutual gravitational interaction. So this is why you saw that the Andromeda galaxy is blue shifted, because the gravitational interaction is dominant in that particular situation, because the galaxy is very close by to us. But for the other galaxies, this expansion is more dominant, so they are red shifted, right? Right. And this graph right here that we have, the slope of this graph can not directly equal the Hubble constant, but this can be related to Hubble constant or the Hubble law. So let me see. The Hubble law is expressed in this way: H naught equal V over D. V is the galaxy's recessional velocity, and D is the galaxy's distance in terms of megaparsecs. And remember, these units are very important when you use this Hubble's law, right? V, the velocity has to be come in terms of kilometers per second, and the distance to the galaxy is megaparsecs. And once you plug these values V and D here, the value of H naught will come out, and H naught is the Hubble constant. Now, if you look at this graph right here, the y-axis is this axis right here, and the x-axis is the distance in terms of megaparsecs, which means if you take the slope of this graph, it will give you the velocity, recessional velocity v over d. And this equation is actually, in fact, the slope of that graph, v over d. And Hubble constant, the units of the Hubble constant comes in terms of kilometers per second per megaparsec. So make sure you keep an eye on these units, because these are something not that we used to have in day-to-day life, right? And assume that the Hubble law is same everywhere. The Hubble constant is universal fixed quantity. So if we assume that the Hubble law is same everywhere, which means if you have the same expansion rate, of course this is not the case if you go into deeper in the subject, but if that is the rate is the same, we can assume that the Hubble constant is a universal fixed quantity. But actually what has happened is this can evolve with the rate shift or with the time, right? And this is again the same graph. And to measure the Hubble constant, what you need to do is you have to find the recessional velocity that can be measured to a very high precision, particularly for distant galaxies, which actually the galaxies are less affected by the local galaxy motions, because when the galaxies are far away, the gravitational interactions are low, so that the effect of recessional velocities can be measured to a high precision over distant galaxies. And the distance measurement are much more uncertain. Many techniques have been used to measure the distances to these galaxies. One way of measuring distances is using Cepheid variables that we talked in the previous lectures. And also you can use carbon detonation supernovas to measure the distances. And remember, for this particular purpose, you cannot use parallax method, right? Remember that there is a practical problem with the parallax method, because when the distances are larger, the parallax angle gets smaller, then you cannot use that to measure distances for very large, the objects that are far away, such as galaxies and galaxy clusters. And these distance estimates have an accuracy of 10 to 20%. So which means Hubble constant accuracy also depends on these distance measurements. And current estimate for the Hubble constant is 74.3 plus or minus, and the error is 2.1. And again, keep in mind about this unit that you have here, kilometers per second per megaparsecs. Now, if you need to measure these things practically, this is what we would do, right? Using the redshift, we can estimate actually the distance, given that we know the Hubble constant. Now, if you know this Hubble constant right here, H naught, we can actually measure the distances to the galaxies. Now, how we would do that is, first thing is you need to obtain the spectrum of the object that you are interested. For example, if you need to measure the distance to a particular galaxy, go out and take a telescope, go to a telescope and take the spectrum of that particular galaxy. And from the spectrum, you can get the redshift, right? So once you have the redshift, you can convert that redshift to a recessional velocity, right? This basically counts in terms of there is a relation that I also showed that this was in your notes as well. There is a relation that you can convert the redshift into a recessional velocity. So this is how you find the recessional velocity, and once you know if assume that if you know the value of the Hubble constant, then you can find the distance using the Hubble law, which is V over H naught, right? And basically, let me see whether I can give you this value of the, I guess this T naught. It should be something like delta lambda over lambda or something like that for the redshift. And then you need to take that and convert it to the recessional velocity. So that's how you do it. And I was actually planning to do one of the exam practicals using that software to measure these practically using a virtual telescope, which we actually may not have time now. And this is now you would have another new method to find distances to different objects, right? This is using the Hubble's law. And this technique has been used by astronomers to map out vast regions of the universe. And this is the currently only useful method to estimating the distance to remote objects such as quasars. Quasars are like one type of, we call as active galaxies, which we didn't talk. Just go and Google it, you will find the definitions of quasars, which are very distant, that has very high redshift, which means they are pretty much far away from us. Right. So those information that we take from the Hubble's law gives us that the universe is expanding. And now we know another method of finding distances. Once you know the Hubble law and you measure the spectrum of a galaxy, you can find the distance using the Hubble law. Now, in recent years, astronomers have actually carried out very large redshift surveys, which means you basically take the spectrums and find the redshift of those galaxies in the universe. And from this, what we have learned is that the great deal about distribution of galaxies. Remember that last slide, I told you that once you have the redshift values, you can convert it to the recessional velocity and then use the Hubble law to find the distance. So astronomers actually have used this method and they did large redshift surveys. So the aim is to just to find the redshift using the spectrums of those galaxies. And they have actually learned a lot of information about the distribution of galaxies in the universe. And so what they have found is galaxy groups, clusters, and superclusters are very common in the universe. So there are a lot of those. And the structure is they often make up enormous walls and filaments, and some of which are at least 200 megaparsecs in size. So they make these large structures, right? And surprisingly enough, there are also some enormous voids which contains very few galaxies. And there are places that we called as voids that has very few galaxies, and at the same time there are places that you have these large walls and filaments that contains very large sizes like 200 megaparsecs. And these structures indicate that the presence of large empty bubbles in space with galaxies found around the edges, right? So if we have the picture, okay, this picture will probably explain what I have mentioned in the previous slide, that you have this wall type of structure, and this one actually right here is this set of dots we called as great wall, right? A collection of galaxies and clusters, and our galaxy is right here. And this is one of the redshift surveys that they map all these galaxies. And remember, you can see that they are not evenly distributed, all these structures. So you have voids, which means places that you don't have much galaxies, and then you have these filament-like structures, right, on the universe. So these comes in using those large redshift surveys. Now, the fact that the universe is expanding implies that the things were closer together in the past. So what this estimate of the these facts that we have in the about the universe is expanding implies is that all these things were actually together, very closer together in the past, right? And we can use the Hubble constant to estimate the age of the universe itself, if you need. Right now, the universe is expanding, but if you go back in time, or if you make a movie, or if you rewind what has happened in the past, what you would see is all these galaxies will go into a single point, right? Because now they are expanding, but they were very close to each other in the past, maybe millions of years ago. Now, see, if you know the Hubble constant, you can use this Hubble constant uh, to actually predict the age of the universe. It is not a huge calculation, just using a simple calculation. Uh, using a very simple calculation, you can actually predict the age of the universe. And I will probably leave this for you as an exercise. This is not that much hard. So the measurement of the Hubble constant tells us how fast the universe is expanding. If you assume it expanded at the same rate, the only problem here is we assume that the expansion rate is the same for the whole period. So we can estimate that how long ago everything began moving away from everything else. Now, assuming Hubble constant value of the Hubble constant is 74 kilometers per second per megaparsecs, you can think that how long would it take to travel 1 megaparsec at a rate of 74 kilometers per second. And just find the answer for this one. This is just a simple calculation, so I will just leave it for you. The answer you will get is around 14 billion years. And this is actually a rough estimate for the age of the universe, right? So I expect that you can do this yourself, right? So all you need to do is just take 1/, each note and then convert everything to just do the unit conversion, right? Convert everything to years, so you will get the idea. Right. Now, as all the information that suggests for us is we have this structure at the end, but what we know is universe keep expanding. Now, in the past, we know that from the Hubble constant, we have a rough value for the age of the universe, which is 14 billion years. Now, what we know is that the universe is expanding from the beginning, right? So then there should be a point that all this matter uh, are concentrated to one single point, where the point that the expansion has begun. Now this is where we have the Big Bang. So the Big Bang is that the preceding estimate that the universe was very dense about 14 billion years ago, because all the matter that you see expanded right now should have concentrated into one single point 14 billion years ago. So which means at that particular point, the universe was very dense and very crowded, right? Because all the matter is concentrated. And so in fact that it appears that the universe itself began at this time, at that time. So we used to tell that this is the time where the universe has begun. The universe is thought to have begun with a huge explosion known as the Big Bang. So this is what we actually predict now. So there was a one single point, and then we have a huge explosion known as the Big Bang, and then universe started to expansion from there, right? Begin the expansion of the space. So this is what we called as Big Bang. You probably have heard this name before. Now Hubble's law tells us that the universe is expanding everywhere we look. So any direction we look at, the universe seems to be expanding. So this implies that there is no special location in the universe where the Big Bang originated. So you can't tell that this is the location where it is originated, right? That it basically took everywhere, right? So basically the universe does not have a center. Right, the redshift that we seen in the spectra of distant galaxies is due to the expansion of the universe, and we talked about this before. From the Hubble law, the expansion, the redshift that we basically see is due to this expansion of the universe. That is about movement of the galaxies through space, not because of the relative movements with respect to one galaxy. And this redshift has actually a name called cosmological redshift. And remember, the redshift that we have due to the relative motions we called as the Doppler redshift. And due to the expansion of the universe, there is a redshift that we used to talk from this Hubble's law. This is called as the cosmological redshift. Remember, these are two different things, right? And you probably have heard before, there is something else called gravitational redshift that basically due to these gravitational effects come into play, especially in very close to the black hole, you have this gravitational redshift. That's basically due to the curve of the space-time close to a very huge mass. Right, so now the next question is, now we know that the universe has expanded at a particular point like that. And so there is a small disturbances here. Just give me a minute. Just give me a minute. Right, so I'm back here. So sorry about that. And right, so what we have talking about that the universe has begun actually 13 billion light years ago with this huge expansion, which we call as the Big Bang. And since then, the universe has started to expand and it continues to expand, right? Now, because of the technology that we have in current, we can look for very large distances. And it is now possible to see galaxies that are actually distances approximately 13 billion light years away. So we are also able to see the distant galaxies and quasars and radio galaxies. And these are actually, I did not talk in the class what a quasar and radio galaxies. These are actually a type of active galaxies which are very far away from us with very high redshift values. The higher the redshift means these are very far away objects. And the interesting thing is, when you look at these high redshift values, the universe looks completely different, right? Because even if you look at galaxies, their shape is completely different as well. The things that we are seeing very nearby, the shapes are, we can tell that they are spiral and those kind of stuff, right? Elliptical, spiral like that. But if you look at this very high redshift universe, when you go close to the beginning of the universe, to the age where these galaxies started to evolve, their shapes are completely different. And they are, in terms of shapes, they are very irregular. And they are forming stars which much higher rate at that time than now. And galaxy interactions are appear to be common, as you expect, because it just started to expand at that time, and the quasars are far more common than they are nearby. And the observations are all consistent with the Big Bang, right? So the interesting thing is this theory called Big Bang theory, that we believe that everything started at a particular point after this huge explosion. So that what explains in the theory is very much consistent with our observations. from the telescope. So that's the important point here. Right, so let me, right. Another thing that we predict is after this Big Bang, at very early universe, that there must have been the universe should be very dense and hot place, and then it would have been filled with very high energy radiation giving off a black body spectrum. So this has happened very early times. At very early times, the universe was very dense and hot. So which means when it is very hot, there should be the temperature is around greater than 1 billion Kelvin, and uh, they would have been filled with very high energy radiation at that time, giving off a black body spectrum. So for this black body spectrum had a temperature greater than 1 billion Kelvin at that time. But what has happened was it should be possible for us to detect this light now as it leaves the edge of the observable universe. Now, if you have that radiation at that time after the Big Bang, we now should be able to detect that radiation, right? So that's the idea. But the only thing is now, since with the expansion of the universe, this radiation should be greatly redshifted, and measurements have shown us that the radiation should be now in the microwave wavelength range, right? And the temperature should be around 3 Kelvin, and this is predicted from the Big Bang, right? So what we need to have is, here is a graph that again shows that at the first instance, this background radiation is around this particular wavelength, and you can see when the temperature drops, with the expansion, the wavelength has shifted to radio wave range right here. So the prediction was that in 1948 that the universe should be filled with this leftover heat of the Big Bang, which we now called as the microwave background radiation. And also there is this name, the name is also given as cosmic microwave background. And there were two American scientists who were named as Penzias and Robert Wilson, who actually used radio telescopes to study the Milky Way. So they were actually not looking at this background radiation, but they were the people that eventually found this after the background radiation of microwaves in the microwave region, which actually became a very strong support for the Big Bang theory, because Big Bang theory expected this microwave background radiation redshifted to this microwave sorry, let me go back to the previous slide. Yes, so what has happened here was the Big Bang actually theory itself predicted this afterglow of radiation, which should be redshifted now to the microwave region. And these scientists have found that. 1964, in fact, they got the Nobel Prize for this finding, figuring out this, or the discovery of the cosmic microwave background radiation. And after that, there were a few satellites that went into space specifically to measure this cosmic microwave background radiation. The primary reason is that when you measure it from here, sometimes you get the effect from the atmosphere. So avoid that, you send satellites to the outer space to measure that. The first one was called K.V.S, which first measured this cosmic microwave background radiation. And this image that you are seeing here right now is actually coming from the Planck satellite that came from around 5 years ago. So they sent this second satellite to measure it more sensitively. The different colors that you see is actually the very smaller variations that you see in the cosmic microwave background even. And from these results, they have predicted the value of the Hubble law as 67.8, which is the latest updated value. And the age of the universe from this value was actually 13.79 billion years, right? So that's the information what we have up to now. And this picture actually summarizes everything that we have learned up to now. Here is where you have the Big Bang, time is 0. So this is where the time began. So that's what we predict. And then the temperature was infinitely large at that time. And then there was this sudden explosion of a single point. And then everything was expanded after that. And this graph actually explained everything uh, from a timeline after 10 to the power minus 32 seconds. This is, you can see the time span is very small at this time. We have something called inflation. So this is actually a different theory which we have as inflation theory that explains what happens right after the Big Bang. So inflation theory basically explained there was a very huge expansion of the universe within a very short period of time at that particular time. And then after the expansion, after the inflation, we have this formation of deuterium and helium at a particular point. And then you have this cosmic microwave background after some time. And then there is a era that you have a radiation matter era, which we called as that. And then cosmic microwave background started to scatter. And this is where the point that you see the light. This is the present time that you have these galaxies, different types of galaxies. And this is the point that the last photons scatter, which means everything that you can see from a telescope will be up to here. And before that, you cannot see, right? And this is very similar, but if you look at up in the sky, if you have cloud layer like this, then you can't see anything beyond that. So the same thing happens for the universe as well, basically because of this scattering effect. So light gets scattered from here so that you can't see. The same thing happens here. And this is actually, if you go into details, I can explain you how these first atoms like hydrogen forms and converted into helium, those kind of stuff. But for the time being, I am not going to go into too much details about this, but make sure that you understand this big picture about the cosmic microwave background and how the Big Bang occurs. And after that, there is an inflation region, which is a sudden expansion of the universe. And then for different times, you get cosmic microwave background, and then you have first photons emitted that you see right now. And like that, there is a process that this has happened. Right, and also these two graphs also tells you something about the radiation and matter era in the universe. And you can see this axis right here is the time since the Big Bang, and this is the point where the Big Bang started. And then you go in the x-axis with the time, and then the y-axis is the density of the universe, kilograms per cubic meters. And you can see this the blue shapes graph at the beginning. So this is where actually the radiation dominated. Most of the things are radiation, and then there is a point that you will get a matter-dominated universe, which is the universe now we are living, because the matter density is larger compared to radiation density. Right, so that's so there is a time that the idea is time that there is a right after the Big Bang, you basically have a radiation dominated universe, and it gets converted to matter dominated universe after some time. Right, so this basically this graph basically tells you how this helium and deuterium, so they are formed, how these first atoms or the production of light elements after the Big Bang with the process called primordial nucleosynthesis. And then what happened before the Big Bang, right? So this tells you, so if you think about, just to get you an idea what happens before the Big Bang, actually there is no answer for that. So all of the available evidence indicated that the Big Bang event occurred in the past. So some of you may have a question, what happened before that, right? So if you go backward in time towards the Big Bang, the universe gradually becomes denser and hotter. And eventually the universe would become infinitely dense and hot. The matter itself could no longer exist. And what happens is at this particular point, all of our laws in physics would break down and we could not predict what happened earlier. So this is what happened. So so the Big Bang represents the birth of universe itself and the time itself, right? So that's what we believe. Now the next question is, in the cosmology, what will happen to the universe in the future? Will the universe expand forever or will it stop? Those kind of questions, right? And that depends on a parameter called critical density, which you can measure for our universe itself. And depending on this critical density, which we called as omega parameter, depending on the value of this density, the fate of the universe will be decided. And this is what possible futures for us. So after the Big Bang, here is where the Big Bang occurred, and depending on, so this is where we are right now, and universe can expand and then can converge again or come back again to the same point, which we call as a big crunch, or universe may be marginally bound or unbound, right? Right. I guess there are few things that we can need to discuss. If time permits, I will discuss these things in the next day. But let me go through some of these things very briefly. Maybe now from the Big Bang theory, there were some problems that they had or they couldn't explain from the Big Bang theory at the beginning. That we told that there is a sudden explosion and everything got expanded. And so one of those called as the horizon problem, and there is another one called flatness problem, which we couldn't explain using the Big Bang theory. Now, as a result of that, and a scientist called Alan Guth from the MIT University, he is the one actually who introduced this era of the inflationary universe that he believes that has happened from after the Big Bang, after 10 to the power minus 35 seconds, up to 10 to the power minus 32 seconds. Within a very short period, he assumed that the universe has expanded from this value right here to this value right here, which is an exponential growth of expansion. And this is basically to explain these two problems, which one is called as the horizon problem and the other one is called as the flatness problem, right? And let me see, if time permits, we may talk about these things future, but I have put the information here just to give you a rough idea that these things are here so that you can come back and study these later if needed. Now, and this region right here, we call this gut epoch, so which is also as called as grand unification theory. Now we know that there are four basic forces in the universe: electromagnetic force, weak force, gravitational force, those kind of things. But even at the very beginning of the universe, we used to tell that all these forces are unified together. And after some time, they started to break down to different forces. For the weak force, electromagnetic force, gravitational force, like that, right? So that's what it means. Right, so this basically tells you some ideas about the inflation. And you can see here is the place that the Big Bang occurs, and after some time, at the beginning, it started to expand very exponentially, and then it expands with like a constant rate up to right here. This is what we have today. But after that, there is a quark soap, and then origin of protons and neutrons first occurred, then origin of the light atomic nuclei right here, and then origin of atoms after some time, and then first galaxies are formed, and we have galaxies right now. And here is the time frame as well. So these pictures basically explain briefly the whole story. And then there are experiments that are going to established to measure the changes in these expansion rates as well. And what we have right now is actually universe is now accelerating right here, and this is what we have as a result of now. And this acceleration is, we believe, coming from the dark energy. And remember that there are normal matter in our universe, and there is dark matter we talked inside galaxies. And then there is dark energy, which is responsible for this new acceleration of the universe. Okay? There are three things. And if you think about the density, normal matter only contributes 5%, right? Dark matter 25%, and 70% of comes in terms of the dark energy. So that's what has happened. And these graphs are basically summarizing all these things. And what we can conclude now is 95% of the universe is we don't know, because we only work with matter, and only 5% of the universe made up of this matter, right? And 95% of the things we don't know too much detail, especially about this dark energy and also the dark matter. Right, so I just quickly went through all these things due to the time limitations, but the information are here. Just go through and look at it, and make sure that you complete those tutorials. And I will have a class around next Monday to discuss briefly about those two tutorials, and also the solutions will be posted after Sunday once you have submitted the tutorial. So I expect some of you may need to still submit it. So make sure that you go through the notes and also through the tutorials for the final exam, right? So that's all from me. And anybody have any questions? Now, for these sections, I just went through very quickly. There are a lot of details inside that, which will be a very separate lecture series about cosmology. But your syllabus required just like an introduction to cosmology and this Big Bang theory. So that's why I did it. But if you have questions, I can answer now. If not, we can